So one of the things we're going to talk about today is this idea that when we're drawing mechanisms, we're really thinking about induction and deduction. So that's either going from big ideas, right, and then making an inference, or using small pieces of evidence to build up to that big idea. So another way of saying that is a cognitive skill such as inductive generalization from specific cases to something you've never seen before. That's something that we're practicing doing in organic chemistry. And I think that sometimes, right, we have an emotional response when we don't always feel comfortable with what we're doing. And so it's that terrible moment when you stop controlling the situation and start mitigating the damage. I expect that's an all too common feeling in life. And that's part of what organic chemistry is testing. It's resilience, but it's also humility. So if as we're starting to draw these mechanisms, you're still not completely comfortable yet, don't get discouraged. Keep going. This is something that I know that you can do, and we'll work together to make sure that we can practice this. So one of the things that we definitely need to practice drawing are chair structures. So this is a guided practice. We're going to use whiteboards today to do this in class, but you also want to be able to practice doing this at home, because the more you practice this, the more comfortable you'll feel drawing chair structures. So you're going to draw the chair using our parallel line strategy. So the black bonds are going to be parallel to each other, and then the red bonds are going to be parallel to each other, and then the blue bonds will be parallel to each other. And then once we've done that, we're going to draw and label the axial bonds, and then we're also going to draw in and label the equatorial bonds. So the axial bonds, the easiest to draw, they're always going to be vertical. They're either up or down. And if you notice, they alternate as you go around the chair. Equatorial bonds are different. They need to be drawn parallel to the carbon-carbon bonds that they are parallel to in real life. So these are examples of the equatorial bonds that you're going to be drawing. So go ahead and take a moment. If you need to pause, go ahead and draw out the rest of your chair structure. So what is it that I expect you to be able to do with the chair structure? Well, at a level 0, I expect you to be able to recognize planar cyclohexane and dash and wedge diagrams. So cyclohexane with nothing bonded to it, and then a wedge, which is bold, meaning up, or a dash, meaning down. And then I expect you to be able to draw your cyclohexane chair skeleton, and onto that chair, I expect you to be able to draw either axial or equatorial bonds, not bonds that are somewhere in between. When you get to level 3, I expect that you're going to be able to recognize cis and trans on a chair. So remember, cis is on the same side, trans is on opposite sides. Right? The idea is when I do a chair flip, which is what's shown here, notice my methyl group that is up on my chair on the left still is up on my chair on the right, except now it's equatorial, whereas for my chair on the left it was axial. Level 4, right, is being able to draw a Newman projection along any carbon-carbon bond. So we're going to practice doing that today with our whiteboards. And then level 5 is if I had a flat cyclohexane structure and I had a table with A values, I'd be able to figure out what's the most stable structure. And these A values really refer to whatever the substituents are around the ring. So if you think about level 5, right, that's kind of where we're at right now. These are the skills that I expect you to be able to have. Level 7 is where we're going next. So that's our next goal. When we think about drawing chairs, part of what we have to recognize is that these are moving molecules. So at equilibrium, they actually exist in a 95 to 5% ratio, where we favor the equatorial over the axial because of what we refer to as a gauche interaction. So when I have an equatorial bond, I minimize this axial interaction with the hydrogen. So notice, here's my methyl group, here's my hydrogen. This is a gauche interaction. It occurs at a dihedral angle of 60 degrees. When I have my equatorial methyl group, as is drawn here, I have no gauche interaction. So it's less energy to keep that structure. The next thing you're going to get really comfortable doing is drawing chair flips. So the product of a chair flip. So when we're in a chair flip, all axial groups are going to become equatorial, and all equatorial groups become axial. The most important thing for us to remember is that anything is up stays up, and anything that is down remains down. So if we started with axial up, then we would finish with equatorial up. If we started with axial down, then we would finish with equatorial down. If we started with equatorial up, then we would finish with axial up. If we started with equatorial down, then we would finish with axial down. So that's level 7. Now we're going to practice. We're going to practice naming compounds and drawing chairs. And this practice is really critical because it's the point at which, by repetition, you finally feel comfortable drawing these structures and naming the compounds. So go ahead and press pause and go ahead and practice this. You want to check your work. So when we think about chair configurations and converting chair forms into a flat form, that's where we're given a chair and now we draw what's called the Mills projection. And so in order to do that, we have to think about what is up and what is down. So go ahead and take a moment and draw the flat form or the Mills projection. Check your work. So let's go back and think about Markovnikov's rule. So if these were my products, what would be my starting material? Can we think backwards? What do we know we have to have in order for a Markovnikov reaction to take place? We have to have an alkene, and we have to have either some catalytic acid and water, or HCl, or something like Br2 or I2. Well, in this case, because all of my products are hydroxyls, that means I'm probably starting with catalytic H2SO4 and water. Let's think about what our starting materials would be. Today we're going to focus, though, now that we're familiar with the anti-Markovnikov rule, we're going to think about how to use Markovnikov and anti-Markovnikov to make sense of reaction mechanism. So Markovnikov, we know. You always put your hydrogen on the least substituted carbon, and you put your carbocation on the most substituted carbon. Anti-Markovnikov's rule is still a stereoselective addition, but in this case, it uses anti-stereoselectivity. So if we added to an alkene, we would only get the trans product. So an example of the anti-Markovnikov rule, right, is the addition of Br2 to cyclohexene. So this is a mechanism that we introduced last class, but the reason why it's anti is because it has this wedge and dash. So in anti-stereoselectivity, the reactants add to opposite sides of the former carbon-carbon double bond. We know this because one bromine is bonded with a solid wedge, while the other is bonded with a dash. So when we're drawing an anti-Markovnikov reaction mechanism, the first step that happens is the reaction of a nucleophile. So that's where the pi bond, the double bond, acts as a nucleophile to attack the partial positive charge on the bromine, that's our electrophile, to give a bridged bromonium ion intermediate. Then the bromonium is attacked by the other bromide. So this is an ion, it's a nucleophile, and then bromonium is my electrophile. And they form this beautiful anti or coplanar orientation of the addition of the bromine atoms. Another way to be able to show that is to look at the Newman projection to be able to make sense of that. So go ahead and take a moment and practice drawing your reaction mechanism for the anti-Markovnikov rule. Remember, it should have trans as the product. And you can think about drawing the trans diaxial in the chair form. And then you can think about drawing the trans diequatorial, which is the more stable of the two. So those are your two possible products. So it's important for us to remember that either an alkyl group or a hydrogen atom can migrate with its bonding electrons from an atom to an adjacent electron deficient atom. So this is what we call shifts. These are carbocation rearrangements. So in this case, my double bond reacted with HCl, and notice, right, I formed not just one, but two possible products and this second product. That's interesting. Why did that occur? Well, I did a 1,2 methyl shift. So let's take a look at that mechanism in a little bit more detail. So we know this first step. I add a proton. So my double bond attacks my HCl, takes the hydrogen, puts the electrons back onto the chlorine. I form a secondary carbocation. Step 2 is the rearrangement of a bond. That's where one methyl moves to where that carbocation is, forming a tertiary carbocation instead. That goes back to our idea of stability. And then last but not least, our chloride ion attacks the tertiary carbocation to form the rearranged product. So we're going to take everything that you know so far and think about a plausible mechanism for the following reaction. Now, the delightful news is this is a challenge problem. So if you solve this problem and you bring it to class, it is a free quiz for either a Tuesday amino acid quiz or a Thursday mechanism quiz. So you can take your time, think about this, work on it, try and come up with a mechanism. Once you have a mechanism, then go ahead and draw out what it looks like. Show me. If it's correct, then you have a free quiz. So carbocation intermediates undergo three types of reactions. They do rearrangement by a 1,2 shift to a more stable carbocation. Then there's the addition of a nucleophile to form a new covalent bond. And then there's the loss of a proton to give an alkene. This is the reverse of the first step of the addition of HX and the acid-catalyzed hydration of the alkene. So, right, in this case, we actually have three different ways the carbocations can react. The last example we're going to look at is hydroboration and oxidation. So this is the result of the addition of hydroboration oxidation. So that's where I'm adding H and OH across a carbon-carbon double bond. And unlike Markovnikov's rule, the hydrogen always adds to the double bond carbon with the fewer hydrogens, because in this case, hydrogen and boron have different electronegativities. So because the hydrogen adds the more substituted carbon of the double bond and the OH adds to the less substituted carbon, we refer to the regiochemistry of hydroboration oxidation as an anti-Markovnikov hydration. Boron, with the atomic number 5, has 3 electrons in its valence shell. To bond with other atoms, boron uses sp2 hybrid orbitals. And so because of that vacant 2p orbital in the valence shell of boron, BH3, BF3, and other trivalent compounds of boron are always going to be electrophiles. Hydroboration is both regioselective and what we refer to as syn stereoselective. So regioselectivity means that H adds to the more substituted carbon, and boron adds to the less substituted carbon of a carbon-carbon double bond. And the stereoselectivity means that boron and hydrogen add to the same face of the double bond. So that's what we refer to as syn stereoselectivity, as opposed to trans stereoselectivity, where you would add to opposite sides of the double bond. So here's an example of what that looks like. So syn addition, either both on the bottom or both on the top for our stereoselectivity. And the regioselectivity is that the hydrogen adds the more substituted carbon and boron adds the less substituted carbon. So take a moment and practice. See what that looks like. Here's another example of a hydroboration oxidation reaction mechanism that you can draw out, showing the two possible syn additions. And then here's what we're going to do. I want you to think for a moment about this following cartoon. Right, so my goal is not, as poor Calvin has had to do, to memorize information. My goal is really for you to be able to think through the content and make sense of what you know, so that when you see something that's unfamiliar, you can feel confident being able to draw on your knowledge and evidence to provide a reasonable mechanism. Thanks again. Have a great day.